share. And all right, can everyone see and hear?
I can see it.
Yes.
It's there.
You can see it and you can hear. Okay, does everyone got the warm-up factoring sums and difference of cubes?
I have it.
Okay, so I don't know if Mr. Zellweger was able to fit this into advanced functions this year or not, but you can prove that difference of cubes, factors, so a cubed minus b cubed factors to give you a minus b times a squared plus a times b plus b squared. And the proof of it is using the factor theorem. So I'll walk you through that proof. So if you remember the factor theorem, we want to find a number that would make this function equal to 0. And so x is going to be a variable and n is a constant like any number. So if we found f at n here, f at n would be n cubed minus n cubed, which would equal 0. And if you sub a number in and you end up getting 0, it means that x minus n minus whatever number you put in here is a factor, which means it divides evenly into x cubed minus n cubed. And then we're going to use long division. I'm sure Mr. Zellweger was able to fit that in. So long division, we're going to divide x minus n into this polynomial. So x cubed, but then there's no x squared term in here. So if you remember, you add a placeholder plus 0x squared. And then there's no plain x term either, so plus 0x, and then minus n cubed. Then if you remember how long division works, you're going to say, what do I multiply x by to get x cubed? And that would be x squared. X times x squared is x cubed. And I'm putting the x squared above the 0x squared term there, my long division. And then if you remember long division, you're going to multiply x squared by x. That gives you the x cubed. And then multiply it by negative n. And that's going to give you minus x squared n. And then you're going to subtract. That's the procedure for long division. So x cubed minus x cubed is 0. And then this would be 0 minus negative x squared n. When you subtract a negative, you're really adding. So you're going to get x squared n. And then bring down the plus 0x. And then you go to, what do I need to multiply x by to get x squared n? So you'd need to multiply it by xn. And then same thing, xn times x is x squared n. Xn times negative n is negative xn squared. And then we would subtract. And my x squared n minus x squared n is 0. 0 take away negative xn squared is positive xn squared. And subtracting a negative is adding. And then bring down the minus n cubed. And then we're looking at what do I multiply x by to get xn squared? And that would be n squared. Then multiply n squared by x, and you get xn squared. Multiply n squared by negative n cubed, subtract, and you actually get 0 this time, because negative n cubed minus negative n cubed is 0 remainder. So that means that x cubed minus n cubed is equal to my divisor x minus n times my quotient x squared plus xn plus n squared. So that's the proof of how to factor a difference of cubes. If you look at, so here's my, I'm going to put this in a box here. So just like the difference, sorry, put this one in a box here. This is my difference of cubes, but let's rewrite it so that it's in terms of a and b. So a cubed minus b cubed then is going to be a minus b times a squared plus a times b plus b squared. So that's, should have done this in a different color. This is my difference of cubes. And then I could have proved the same thing to you using long division again for a sum of cubes. So this is how you factor a sum of cubes. And you can see that they're very similar. The sign in the middle of the first is opposite, and then this sign's opposite. But other than that, it's the same. All right, so knowing that, what I'm hoping is that you can factor sums and differences of cubes as easily as you can factor a difference of squares. And it's not quite as easy, but it should be get that easy for you. And we use this a lot in evaluating limits, so that's why we're learning it. So the first thing when you look at x cubed plus 125 is recognizing that it's a sum of cubes. Okay, so I would tend to, especially when I'm just learning it, write it out as x cubed plus something cubed. Does anyone know what 125 is as some number cubed?
5.
5, good. Logarithm should have helped you with that. So now we see it really clearly as a sum of cubes. And then we're going to follow this formula. So x is like our a. So instead of a here, I got x plus 5, b is our 5, times our a is x, so x squared minus a times b, so that's going to be 5 times x, which you'd write as 5x, not x5. And then plus b squared, so 5 squared, which is 25. So that would be that sum of cubes factored. And obviously you can go straight to here. You don't need to show that middle one. And also it's worth noting that this term, the quadratic term, can't be factored, okay? So this is fully factored. So for the next example, it's a difference of cubes. So it's really x cubed minus some number cubed. Does anyone know what 8 is as a cube?
2 cubed.
2, good. So that means you're going to be following the difference of cubes. I'll give you a minute to see if you could write out what you think the factorization would be. And then I'll get a volunteer. So you want to follow this pattern here. Anyone think they got it?
Yes, I have one.
Okay, give it to me.
Bracket x minus 2,
Yep.
bracket x squared plus 2x plus 4.
Perfect. Okay, any questions? That's right. Good job. Okay, x cubed minus 1. So that's the same as x cubed minus 1 cubed. So it's a difference of cubes again. So you're following the difference of cubes format. So it's going to be x minus 1, x squared plus, so 1x is just x, and plus 1 squared, which is just 1. And x cubed plus 64 is a sum of cubes because 64 is 4 cubed. So it's going to follow the sum. So it's going to be x plus 4 times x squared minus 4 times x, so 4x, plus 4 squared, which is 16. Okay, so keep this out, so at least you have the formulas. We'll be using them a little later on. So our first lesson today is evaluating limits. We're going to learn to evaluate limits by substitution if possible. That's the really easy, straightforward kind. And we're going to learn to evaluate limits that are said to be in indeterminate form. And for indeterminate form, you have to use procedures to get out of the traps. And I'll talk about what the traps are and all the different ways we can get out of them. The second lesson today goes through just one way of getting out of a trap, but a really important way. Okay, so limits such as the limit as x approaches 2 of x minus 4 are really easy to find because to get the limit, you can just actually substitute x equals 2 to evaluate the limit. So the limit as x approaches 2 of x minus 4. So you can see that in this case, the denominator is at 1. So allowing x to approach 2 doesn't blow up the denominator to 0. Nothing happens. So we can just let x approach 2. And what that means from a graphical sense based on yesterday. Second lesson, here's 2. And we can see that as x approaches 2 from the left, the curve is approaching -2. And as x approaches 2 from the right, the curve is also approaching -2. So just from the graph, you can see that the limit as x approaches 2 of x minus 4 is -2. So whenever we're dealing with a continuous function, so continuous meaning no holes, then you can solve a limit just by substituting. Okay, and mathematically speaking, if a function is continuous at x equals a, again, meaning no holes, gaps, asymptotes, then the limit as x approaches a of f at x is actually just f at a, meaning to find the limit, I can just sub a in for x. Okay? So we're going to try some of those ones, which everybody calls the easy ones. So evaluate each limit. And just so you know, if they're going to be all mixed up, or they would be all mixed up. So your way of testing is it safe to let x approach 3? Okay, and usually in that case, we're looking at the denominator and making sure the denominator doesn't approach 0 as x approaches 3, which is true here. So the limit as x approaches 3 of x squared is 3 squared, which is 9. The limit as x approaches 4 of 2x minus 1. We are able to let x approach 4, so it's just going to be 8 minus 1, which is 7. The limit as x approaches 1 of x squared minus 1. It's just going to be 1 squared minus 1, which is 0. And the limit as x approaches 10 of the square root of x minus 1 is just going to be the square root of 10 minus 1, or the square root of 9, which is just 3. And again, all of these would have graphs that if we looked at them on Desmos, at 4, 2x minus 1 would be continuous. At 3x squared is continuous. Okay, no whole. It's just the limit from the left and right are going to equal and be the value of the function at that point. That's what it means from a graphical standpoint. Okay, and here's a couple more. So the limit as x approaches 2 from the right of 5 minus x squared. So as long as x is continuous at 2, it doesn't matter whether we're going from the left or the right, or just as x approaches 2, which really means we're considering both. And it is, so we can just substitute 2 in. F we'd have to be a little more concerned about because the denominator is not a 1 here. So we really want to test if we let x approach -1, what's going to happen to our denominator. And it's going to approach 1, which is fine. So again, we're fine to just substitute. So once you've substituted, the numerator is going to be 1 plus 1 minus 6, so -4. And the denominator is going to be 1. So the limit is going to be -4. And same with g, it's got a denominator, so we really want to make sure that our denominator is not going to become 0 as x approaches 4. And it's not, so we can go ahead and let x approach 4. So it's going to be the square root of 4 over 16 minus 7, so 9. You remember about square root, you can take the square root of 4 over the square root of 9, or 2/3. So as long as you make sure that allowing x to approach the value doesn't make the denominator 0, then you're fine to just use simple substitution to evaluate the limit. Okay, so now we're going to do something that's really important for first year university. Okay, so I'm going to try to give you a grade 12 understanding of something that you're going to probably spend quite a bit of time on in first year. And that's the definition of whether a function's continuous at x equals a, and what has to be true for you to guarantee that. And a function not continuous, but has a limit that exists at x equals a. So we're gonna use a diagram here. So let's divide our page that we have here into kind of 2 columns. And our first one's going to be continuous. I'm just going to use CTS for continuous at x equals a. And then on our second side, we'll have not continuous, CTS at x equals a. And I'm going to make very similar diagrams on each side. So there's my f at x-axis. Here's my x-axis. And I'm going to make a curve. And that one you can see it's continuous everywhere. There's no gaps in it. And I'm going to choose a place A. It's better to choose it kind of over here. So this point here, it's f at a, you can see that. So that point is the point A, f at a. And I'm going to call this y value, capital L, which you can think of as limit. That number, f at a, is capital L there. The y value on the y-axis. So based on yesterday and this diagram here, we can say that the limit as x approaches a from the left of f at x. So as x approaches a from the left, the curve is approaching L. And we can say that that's equal to the limit as x approaches a from the right of f at x. So we're approaching a from the right. Our curve is again from the right, it's approaching L. So they're equal to each other, and they're both equal to L. So because we know that, we know the limit exists, right? The limit exists. So because of this analysis based on yesterday, the limit as x approaches a of f at x is L. And if this is true and f at a is also equal to L, so these two things have to be true. If they're both true, you can say the function is continuous at x equals a. So if the limit exists and is equal to L, and the value of the function is also L at x equals a, then you can say the function is continuous at x equals a. Now we're going to set up a similar scenario, but where the function is going to be not continuous or discontinuous. So I'm going to try to make my curve look similar, but I'm going to have a hole here instead of just a smooth curve. Here's A. And then if I read over across here, this is going to be L. And then below this hole, I'm just going to put it in the negative so we can spread it out a bit. This is going to be the value of the function when x is a, and we'll call that capital B. So below this hole, this is the point. So here's our setup. We can still see that the limit as x approaches a from the left is going to be L again. And it's going to equal the limit as x approaches a from the right. So we know the limit exists. So the limit as x approaches a from the left of the function is going to equal the limit as x approaches a from the right of the function, and they both equal L again. So we know the limit exists. So we know the limit as x approaches a of f at x exists, and it's equal to L. But the problem is that f at a is not equal to L. What's f at a equal to in this picture?
It's equal to B.
Could it be B?
Yes, it's equal to B. So f at a is equal to B, the filled in dot, right? So because these two are not the same, they're not equal. That means the function is not continuous. And the math word for not continuous is discontinuous at x equals a. And you can see it because there's a hole there. Discontinuous, not continuous. There's a hole there. Okay? Why this is so important is that if a function is continuous at x equals a, you can just use simple substitution to find the limit. If a function is not continuous at x equals a, you can still find the limit. We can see that it exists and it equals L, but it's not going to be as easy as just substituting. We're going to have to use some other kind of algebraic method to find that limit. Okay? So there's going to be a whole theorems on continuity that basically you have to have these two conditions satisfied. The limit has to exist and equal L, and f at a also has to equal L to be continuous. If that's not true, if either the limit doesn't exist or it exists but doesn't equal the value of the function, then you're discontinuous. But that's the grade 12 understanding. If you can understand kind of that definition of continuous versus discontinuous, you're going to be good for next year. Does anyone need more copying time?
Yes, please.
Yep. I know it's a lot there. Anyone have any questions?
So I see on the next line we have there,
Yep.
it doesn't give us a value for -1 x.
Down here?
Yeah, I guess like there is no value for that, but I guess it's just not equal to it because there just isn't a value for it. So
This question, like the next question below.
yeah,
There is a limit. You can see it, right, John?
there is a limit. That's right.
Right. But there, yeah, there's no other value for it. So the picture of this, so if you were to graph this y equals, it would look like that, a line with a hole in it.
Hmm.
Unless you make it into a piecewise function. If you made it a piecewise function, you could assign a value.
Okay.
Okay, but just if you graph it the way it is, it's going to look like a line with a hole in it. I'm just waiting for people to finish copying out the chart here before we move on, and we'll actually answer that question coming up in a minute. Anyone have any questions just basically on the difference between continuous and discontinuous from a graphical standpoint, like what it would look like or what it means graphically?
So, like for the asymptotes.
Yes.
You have an asymptote? the limit isn't going to like become anything, I guess, because one's going up to positive infinity.
Right. So if you had a limit that was where an asymptote was, it would either be infinite or it doesn't exist.
Mm-hmm. So I guess the limit wouldn't exist from either side.
Right.
Yeah.
If you've got a vertical asymptote. Yeah, you can say the limit is positive infinity or the limit is negative infinity, even though you can't actually get there.
Oh, you can say that.
Yes, that's what helps you when you're curve sketching, when you know how to draw how your curves relating to the asymptotes if you're curve sketching. Do you do that in advanced functions?
I think so.
Yeah. All right, so we're going to go on to our next one. All right, so here's when a function is discontinuous at a certain point, it's not possible to find the limit by direct substitution. So here's our prime example right here. If I were to sub -1, I would immediately get 0 in the denominator, so I can't use substitution. Okay, and we can see from our diagram here why that is, and it's because the function is discontinuous at x equals -1. Okay, and straight substitution would lead to 0 over 0. If you sub -1 into the numerator, you'd also end up with 0. And that form, 0 over 0, is called indeterminate form. So 0 over 0 is called an indeterminate form. Okay, and whenever you get an indeterminate form, there has to be another way to solve it, an algebraic method. This one's going to involve factoring, which is the easiest method. So you look at the numerator and see if you can factor it. X squared plus 3x plus 2 is a simple trinomial. So I'm looking for two terms that multiply to 2 and add to 3, two numbers, sorry. So x plus 2 and x plus 1. And now you can divide out the x plus 1s. Now it's safe to let x approach -1. And you get your limit.
Do we have to put in the condition there, or I guess it's kind of already shown that you can't do that? Or
That x can't be -1?
Yeah.
I don't think you can, it's not wrong to put it, but the fact that we're just letting x approach -1 is kind of saying that as well. You can't equal it, can only approach it.
Yeah.
And then if you look at your graph here as well, you can see that as x approaches -1 from the left and the right, the curve is approaching 1, which is the answer we got. Even though there's a hole there. We still found the limit. Okay. So now we're going to get to the fun part. I love doing these limits. They're like little puzzles to me. So when a limit is an indeterminate form, more work in the form of factoring, rationalizing, or finding a common denominator must be done in order to evaluate the limit. So we're going to evaluate each limit, and all of these will end up being an indeterminate form. Okay, so if we look at the first one here, if they were mixed together, you'd first check and see if you let x approach 1, would the denominator approach 0? Yes. So now you know you have to come up with another method other than direct substitution. So factoring is the one I always look for first, especially if it's a polynomial in the numerator. X squared minus 1 is a difference of squares, so it factors to give us x plus 1 or x minus 1 times x plus 1. Now the x minus 1s will divide out. Now it's safe to let x approach 1. So the limit is x approaches 1 of that rational function is 2. For B, it's a limit as x approaches 0 of the root of x plus 1 minus 1 over x. So if I let x approach 0, it's really obvious the denominator is going to approach 0. Factoring is probably not a thing here. Anyone think of what I could do instead? Multiplying by?
The conjugate?
Perfect. And the conjugate is going to be that. So how many people are confident that the middle terms of that conjugate are going to add to 0 if I expand all 4 multiplications out? Most people good with that?
Yeah, pretty confident.
Pretty confident. So you can go to, if I square the first, like multiply the first 2 together, I'm going to get x plus 1. If I multiply the last 2 together, I'm going to get minus 1. And the middle terms I did in my head and they canceled out. Is that okay with everybody? Don't forget to multiply the bottom part together. All right, so then in the numerator, I'm just left with x now, because plus 1 minus 1 divide out. And now I can divide out the x's, leaving me a 1 on top. And now it's safe to let x approach 0. So that's going to give me 1 over, as x approaches 0, that's going to be the root of 1 plus 1, which is going to be a half. Any questions about that one? Okay, C. So let's test out if x approaches 0, the bottom's going to approach square root of 1, which is 1, minus 1, which is 0. So I can't let x approach 0. So this is another conjugate one. This time the conjugate's going to be 1 minus 2x plus 1. This time we're rationalizing the denominator. So the numerator is going to be x times the root of 1 minus 2x plus 1. And the denominator is going to be so if I multiply these two together, I get 1 minus 2x. And then the last two terms together, because the middle ones are going to cancel, minus 1. So we've got x times the root of 1 minus 2x plus 1 over, so I've got 1 minus 1, 0 pair, so I'm left with negative 2x in the denominator. And these x's are going to divide out. So now it's safe to let x approach 0 because the denominator is constant of negative 2. So as x approaches 0, in the numerator, I'm going to get the root of 1 plus 1 over negative 2. Because as x approaches 0, 2x is going to approach 0. 2 over negative 2, which is negative 1.
So say if you have like a number that is going to make it go like irrational or something, where you're doing like a square root of a negative number.
Oh, yeah.
Would you would you have like a limit that goes up to maybe that point where it becomes?
Yeah, you'd have restrictions on it.
Okay.
You'd probably use more advanced rules of finding limits. That would probably be more like first year university, L'Hopital's rule and stuff like that.
Okay.
Okay, if we look at D, there's 4 terms in the numerator. Anyone remember what you look for factoring wise if you've got 4 terms? Remember the factoring flow chart from grade 10? You had 4 terms. What would you look for first?
Factoring by grouping.
Yes, good job. So let's hope it works for us. Probably does. So what's in common with x cubed and 2x squared? X squared is, so we're just going to common factor x squared out of the first 2 terms. Sign that goes next comes next. What's in common with 4x and 8 is 4. Negative 4x divided by negative 4 is x. Negative 8 divided by negative 4 is positive 2. And that looks promising because both binomials are common binomial x plus 2, which I also have in the denominator. So now x plus 2, if you look at these as 2 big kind of chunks here, x plus 2 is in common. And if I divide each chunk, common factor out the x plus 2, I'm going to be left with x squared minus 4. And without even factoring the x squared minus 4, I can already divide out that denominator, which was my problem. So now that my denominator is just 1, I can sub in negative 2. So factor by grouping. Any questions about the 4 we just did? Everybody's good? All right. E is multiplying by the conjugate radical again. So we're going to multiply the numerator by 1 plus 4, root of 1 plus 4x plus, opposite sign from the middle, root of 1 plus x, which means we're going to do the same thing to the bottom. Okay, I'm going to give you guys a chance to say what, or write down what you think the numerator would be if you cancel the middle terms out in your head. And then I'll ask someone to reveal, put the bottom in for now.
I think I know it.
Okay, tell me what it is.
1 plus 4x minus bracket 1 plus x bracket.
Perfect. Yes, that's exactly what I want. The brackets are so important. Thank you. So a negative times a positive is a negative, and then the roots cancel and you're left with 1 plus x. Perfect. Okay, so now we can keep going from there. So that minus distributes through the bracket. So minus 1 minus x. And then my 1 minus 1 add to 0. 4x minus x is 3x. And now I can divide out those x's. So it should be safe now for me to let x approach 0, because the denominator now is going to approach the root of 1 plus the root of 1, which is fine. So if I let x approach 0, the numerator is going to stay 3. The denominator is going to be the root of 1 plus the root of 1. Or those are both 1, so 3 over 2. Okay, F. Limit as x approaches -3 of x plus 3 over x cubed plus 27. So this x cubed plus 27 is a sum of cubes, which we just learned how to factor at the beginning in our warm-up. We didn't already know. So that's what we're going to do. So it's going to be the limit as x approaches -3 of x plus 3. And then see if you can factor that sum of cubes. Remember, that would be like x cubed plus some number cubed. And who knows what 27 is as a cube.
It's 3 cubed.
3 cubed, good. Okay, so see if you can figure out what that factorization would be in the bottom. So I'm going back to first page here that had this formula, sum of cubes, and I want to factor it so it looks like that. Anyone think they have it?
I might.
Okay,
Bracket x plus 3 bracket, and then another bracket x squared minus 3x plus 9 bracket.
perfect, yes. Any questions about how to get that? Awesome, okay, so then these divide out, leaving me with a 1 in the numerator. So now is it okay to let x approach -3? Well, I'd have 9 plus 9 plus 9, yep, so it is. So 1 over -3 squared minus 3 times -3 plus 9, which gives me 1 over 9 plus 9 plus 9, which is 1 over 27.
Ms.
Okay.
Northwood,
Yeah,
of the first line of F, where does the 1 on the numerator come from?
when I divided these out, I just wanted to make sure you remember that there's a 1 up there still.
Okay.
Some people, once they divide those out, they forget about the numerator and they just have that. Like as if it's in the numerator. It's a common error I've seen over the years. So just pointing out that when you divide those out, you still have 1 left in the numerator. Okay, G, that one looks tricky. Does anyone have any ideas?
Maybe factor out the bottom as a difference of squares? I don't know.
bottom as a difference of squares?
Or I don't know, you have like the root. Oh, I guess those are both
What does that
root
mean?
rationalized.
What's another way of writing x to the negative 2?
Square root of x.
No, that's x to the 1/2, net 1/2.
Oh, sorry, I think I was confusing that, yeah.
1 over x squared, do you guys agree with that? That
Yeah.
x to the negative 2 is the same as 1 over x squared? Yes or no? I'm using the exponent rule.
Yes.
X to the negative n is 1 over x to the positive n there. Okay? Minus, so 3 to the negative 2 would be 1 over 3 squared, but 3 squared is 9. But that's still over x minus 3. So now in the numerator, we've got fractions to subtract. And you subtract fractions by getting a common denominator. What's that common denominator going to be?
Nine x squared.
Yep, good, 9x squared. So here I had to multiply the bottom by 9, so I have to multiply the top by 9. Here I had to multiply the bottom by x squared, so I have to multiply the top by x squared, but it's still over x minus 3. Now I can subtract the numerators over the common denominator. And then I'm also going to divide by x minus 3, which is the same as multiplying by 1 over x minus 3. Any ideas from there?
Difference of squares.
Difference of squares in the numerator. So you want to go straight difference of squares, 3 minus x times 3 plus x?
Yeah.
Yeah, okay.
Well, I guess we could factor a -1 out of one of them. So then
We're going to have to do that now then, right?
Mhm.
Everybody good? That 3 minus x and x minus 3 are not the same. So 3 minus x is equal to negative x minus 3. That was something we learned in grade 11 when we were simplifying rational expressions. Our overall rule was b minus a is negative bracket a minus b. And that's because if you were to distribute here, you'd get negative x plus 3, which you could reorder, put the positive 3 first and the negative x second, and get back what you started with. Okay, so we call that an identity. And it's a useful identity because it allows us to divide out that problematic factor in our denominator. So I'm going to use that now, my next step. So I'm going to change this to the limit as x approaches 3 of negative x minus 3 times 3 plus x over 9x squared times x minus 3. And now I can divide out these x minus 3's. So I'm left with the limit as x approaches 3 of negative brackets 3 plus x over 9x squared. So now it's fine to let x approach 3. It's going to give me negative 3 plus 3, so negative 6 over 9 times 3 squared, which is negative 6 over 81, which reduces to negative 2 over 27. So that was a tricky one. That one, we needed a common denominator. We needed a factor. We needed to use this identity so that we could divide out and then finally substitute. And we had to reduce our fraction in the end. Okay, H is a cool one. Look at it, see if anyone has any ideas. So I can't let H approach 0 because the denominator would be 0. Any ideas? If I told you the numerator was a difference of cubes, would you believe me?
Yes.
Yes. We
Yes.
trust you. We believe you.
A would be 4 plus H. Everybody good there? And B would be what number? What number cubed is 64?
4.
Yes. All right. Yes. So this is a fun one. So if we follow the A cubed minus B cubed, I'm gonna find that sheet here. Here it is. We follow that difference of cubes. The first one is A minus B. So our A is 4 plus H minus our B, which is 4. And you can already see that 4 minus 4 is going to make that just H, which is exciting. And then the next one is A squared. So I'm just going to write that as 4 plus H in brackets squared. I'm not going to expand it out or anything, because this is the really important part here. This is what's going to allow me to divide out that problematic H in the bottom and then let H approach 0, which is going to make these easy. Okay, so that's my first term, and then I need plus A times B. So plus A times B. So that's going to be 4. That's my B times 4 plus H. And then plus B squared. So 4 squared is 16. So that's the numerator factored as a difference of cubes. So 4 plus H minus 4 is just H. And now I can divide out the H's. So we got out of the trap. And now it's safe. The denominator is 1, so I can let H approach 0. So I'm going to get 4 plus 0 squared, which is 16, plus 4 times 4, which is 16, plus 16. So it's going to be 48. Any questions about that one? Okay, our last one. All right, this is a fun one. Any ideas? We'll put a little prompt there.
Let's rationalize this one.
Okay, so I'm going to first rationalize the numerator. We're going to do a double rationalization here. And then I'm going to rationalize the denominator. So again, this is really just multiplying by 1, and so is this. So I've multiplied by 1 twice, which is fine. And then when I decide how to do my multiplications, you guys are getting good at these now, I'm going to FOIL these two in the numerator, but in the denominator, I'm going to do the FOIL on these two. And then just leave whatever the other one is multiplying at the end. So if I multiply 2 minus root x times 2 plus root x, what am I going to get? I'm going to keep it in brackets. I should keep it in orange brackets to be nicer. If I multiply 2 minus root x by 2 plus root x, what would I get?
Four minus x.
Yeah. So if I just multiply these two together, I get 4 minus x, but I'm still multiplying by 3 plus root 2x plus 1. So that's my numerator. Now, what about if I multiply these conjugates together? What am I going to get?
A 9 minus in brackets 2x plus 1.
Nice. And then I've still got to multiply that by 2 plus root x. Okay, so the numerator doesn't look like I've really got anything to do with right now. So I'll leave it as 4 minus x times 3 plus root of 2x plus 1. But in the denominator, I can expand that bracket there. And I'm going to get 9 minus 2x minus 1. So the 9 minus 1 is 8. I still can't let x approach 4 because I'd get 8 minus 8 here. Does anyone see anything I could do?
Factor it.
I can common factor in the bottom. So 8 minus 2x has a common factor of 2. So if I common factor 2 out of here, I would get 4 minus x. And now these 4 minus x's can divide out. So now it's going to be safe. To let x approach 4. So if you let x approach 4, the numerator is going to become 3 plus the root of 9. Because 2 times 4 is 8, plus 1 is 9. And the bottom is going to become 2 times 2 plus root of 4. So that's going to be 6/8, which you can divide top and bottom by 2, or 3/4. So that's a double rationalization. Any questions about any of the steps on that one?
How did you go from step 2 to step 3 in the denominator?
Step 2 to 3 in the denominator. I multiplied that -1 by the 2x and by the 1.
That still doesn't make sense. Where does the 8 come from?
Oh, you step 3 to, okay. So see the 9 minus 1 is 8. 8
Yeah.
minus 2x. So I collected the 9 and the -1 and made 8. Does that make sense?
Yeah.
Okay. Any other questions for this one? Okay, stay on. I want to talk about the next lesson. Actually, no, I'll do that. I'll do that right now. So the next lesson is on more evaluating limits in indeterminate form, but it's specifically using this change of variable to create a simpler equivalent limit. It's really cool. The video explains it really well, but if you're having trouble, like you can see the questions look more complicated, then please either hop on the Google Meet, and if you don't see me, then Edsby message me, and I'll arrange for us to get back on the Meet and try some together. I think you'll be fine. Just make sure you work through the video. If you're not able to get your assignment in by 4, just give me an Edsby message so that I'm not looking for you and I know that you've still got to hand it in. Is everybody good with that example, and I can stop recording?
Yeah, I think that's all good.
That's all good? Okay, I've got another thing to mention. I noticed that when I converted my file and uploaded it the first time, so when you got all those ones together, I did my older file, so I didn't have the answers. So if you want just the answers, there's another page. If you look at the newer file I posted last night that just has the final answers. You should go and look at form and stuff like that, but if you just want the final answers, it's there on the very last page of each file. Okay. So it's there. I updated it last night, and it would just be one page to print out. But if you don't have access to a printer, I can take a snap of them and put that on our Edsby feed as well. Okay. All right, I'm going to stop recording. Stop recording.